Good day to my respected teacher. I'm Jaina Naurin and today I'm going to give a presentation on post-quantum cryptography. So a quantum computer is a type of computer that uses the principles of quantum mechanics, physics of subatomic particles to process information. Unlike the classical computers which uses bits 0 or 1, quantum computers they use qubits and this can be in 0 or 1 or both at the same time. Classical security like RSA or ECC depends on problems that take billions of years to solve with normal computers. So a quantum computer can solve all these in much faster way in minutes or hours using algorithms like Shor's algorithm which breaks RSA or ECC and AES also. So let's have a look into cryptography algorithms. So RSA, reverse Shamir Adelman, its type is asymmetric encryption. It's a public key cryptography. Its purpose is to secure key exchange, digital signatures, and authentication. And its key generation, we choose two large prime numbers, which we'll be seeing in the upcoming slides in detail for RSA, and compute ILOs and select private and public key, and then we encrypt and decrypt the message accordingly. And its limitation is that it is very slow for bulk data. It is used mainly for key exchange, not for actual file or data encryption. And for ECC, ECC is elliptic curve cryptography. It is asymmetric encryption like RSA but based on elliptic curve mathematics. And its purpose is same as RSA to secure key exchange, digital signature and authentication and how it works. We will be seeing that in brief in the next slides. So in limitation is that it's more complex math than RSA. It is not as widely adopted historically, but it is gaining dominance today. AES, Advanced Encryption Standard, it is a symmetric key algorithm used for encryption bulk data. Example like Wi-Fi and VPN files and etc. are all come under AES. Let's go to reversed Shamir Adelman. So here we'll be taking two large prime numbers P and Q, and then we'll be computing modulus n equal to p times q, and then we compute Euler's function psi of n equal to p minus 1 to q minus 1, and then we also the next part is we get the public exponent that is e, and e's value will be greater than 1 and it will be lesser than psi of n, and the GCD will be the GCD of the public exponent e and psi of n will be equal to 1. So, and then we compute private exponent d such that d times e is congruent to 1 mod psi of n. But generally the formula is d equal to e inverse mod of psi of n. But to make the calculation a bit easier, we do d times e congruent 1 into mod of psi of n, and then we get the public key. Public key you'll be taking the form of e comma n. Private key you'll be taking the form of d comma n. And e and d already we have got the values. For encryption of ciphertext, we use C congruent m power e mod n, and m is a value which is lesser than n. And when it comes to decryption, we'll be using the formula m congruent c power d mod n. This is how RSA works. So, elliptic curve cryptography is a type of public key cryptography. It is based on the mathematics of elliptic curves over finite fields. So, instead of relying on very large prime numbers like RSA, ECC uses properties of elliptic curves to create secure cryptography keys. The main advantage is smaller key sizes, same security, and strength. It is same security and strength as RSA, but it is faster and lighter. The math behind ECC is kind of simplified. I'm giving you a short brief of it. So an elliptic curve is defined by an equation like y square equal to x cube plus a times x plus b, where a and b satisfy certain conditions to avoid singularities. So on this curve, you can define a group operation. Adding 2 points gives another point on the curve. Multiplying a point by a number means adding it to itself multiple times. Okay, and this is how ECC works. And coming up with the uses of ECC, ECC is widely used in modern cryptography, especially where efficiency and performance matters. And encryption protocols, and when it comes to encryption, protocols like elliptic curve integrated encryption scheme uses ECC for secure message encryption. Digital signatures, it uses elliptic curve digital signature algorithm ECDSA is used here. And it is mostly used in Bitcoin and Ethereum blockchain transactions and all. So the next uses of ECC is key exchange. So elliptic curve Diffie-Hellman, it is ECDH, allows two parties to secure generate a shared secret over an insecure channel. It is used in TLS, HTTPS, VPNs, Signal, and WhatsApp encryption. Next uses authentication. It is lightweight devices like IoT, smart cards, embedded systems use ECC because of its smaller keys and lower computation needs. Blockchain and cryptocurrencies. Bitcoin, Ethereum, and most cryptocurrencies use this curve with ECDSA for secure transactions. Next is AES, Advanced Encryption Standard. It is a symmetric block cipher. So symmetric matlab the same secret key is used for encryption and decryption. And block cipher, it encrypts fixed size blocks of data always in 128 bits or 16 bytes. Key sizes can be 128, 192 or 256 bits. This decides the number of rounds. Steps are, first step is key expansion. The input secret key is expanded into multiple round keys. One round key is used in each round of encryption. Second is the initial round. You add round key XOR. Okay, we use bitwise addition, the plain text block with the first round key. And the main rounds NR minus 1 times. Each round has 4 steps, okay, sub bytes. Each byte in the 4 cross 4 state matrix is replaced using a fixed XS box, a substitution table. Provides non-linearity, okay, that is harder to predict relationships between plain text and ciphertext. Then we have shift rows. Rows of the state matrix are cyclically shifted left by different offsets. This mixes the position of bytes to spread information across columns. Then we have mixed columns. So each column is transformed using matrix multiplication in the finite field. This mixes bytes within each column so that the changes in one byte affects all others. Add round key, XOR the current state in the round key. And next is the final round. Same as the rounds, except mixed column is skipped. Steps are you go to sub bytes, then go to shift rows, and then add round key. This is how AES works. Next, quantum threat. Quantum algorithm make today's cryptography vulnerable. Okay, RSA or ECC can be broken, and AES is weakened, demanding a shift to post-quantum cryptography. Post-quantum cryptography, also called as PQC, is not about building quantum computers, it's about building cryptographic systems that stay secure even if powerful quantum computers exist. PQC algorithms are designed so that the Shor's algorithm and the Grover's algorithm don't give attackers an advantage. For example, RSA depends on factoring. Shor's algorithm breaks it really easily. Lattice-based cryptography, on the other hand, that is the PQC cryptography, it's a technique. It relies on problems like the shortest vector problem, which are believed to remain hard even for quantum computers. The US National Institute of Standards and Technology is leading a global standardization process to select and recommend PQC algorithms. Once standardized, PQC will replace RSA or ECC in protocols like TLS for HTTPS, VPNs, and secure mail, as well as in digital signature and blockchains. This transition is urgent because the data stolen today that is encrypted with RSA and ECC could be stored and decrypted. So in the future, once again, quantum computers are available. So as you can see in front of me, there is a picture. So in classical cryptography, you can see that for level 0 and for level 1, that's how the classical cryptography works. But then when we use PQC, post quantum cryptography, level 2 and level 3 are also there, which helps in more stronger encryption of data. So level 2 we can say PQC, post quantum cryptography keys establishments only happens. It is signal with PQ XDH. And then in level 3, we can see PQC key establishment and ongoing PQC rekeying. So this makes it more powerful. So now let's see types of PQC algorithms. The first algorithm is lattice based cryptography. So imagine a giant forest with millions of trees, and now you're told find the shortest tree in this entire forest. In a small forest, you could do it, but in a forest with 500 dimensions, it's impossible to even see where to start. That's what makes lattice problems hard, and why hackers, even with quantum computers, can't solve them really quickly. The core idea is the security comes from lattices. A lattice is like a grid of points in a space. So in 2D, you can imagine it as dots arranged in repeating pattern like tiles on the floor. So in lattice cryptography, we use lattices in hundreds of dimensions. Problem that are easy in 2D or 3D becomes nearly impossible in high dimensions. This hardens is what makes lattice cryptography secure. And the hard problem is that two important problems like lattices. Okay, shortest vector problem. And imagine just standing in a huge grid of points. You need to find the shortest path to a non-zero point. In high dimensions, this becomes extremely hard. Second is learning with errors. So imagine solving a set of equation like 2x plus 3y plus 72x or which is equal to 72x plus 3y, and that is also equal to 72x plus 3y equal to 7. I'm giving you an equation. But each equation has a tiny mistake added. Without the secret key solving these noisy equations is very difficult. So both SVP and LWE are believed to be hard even for quantum computers. This scheme, NTRU, so one of the first practical lattice based systems. It was introduced in 1996. Okay, so it works well for encryption and key exchanges. So modern lattice scheme chosen by NIST as the standard scheme. So it's very efficient, very secure, and very practical. It will replace RSA and ECC in protocols like TLS. Advantages is very fast, it's well studied. Researchers have been testing it for over 25 years, and the chosen standard is also very good. It is flexible. And disadvantages are larger key size like RSA, it's a few kilobyte. In ECC, it's even smaller. But lattice based, typically a few kilobyte or tens of kilobytes. Still larger than ECC, but it's practical for modern computers. Next we have is code based cryptography. So imagine you write a message in a book, but then you intentionally add hundreds of spelling mistakes. To everyone else it looks like gibberish, but your best friend has a secret dictionary that tells them exactly how to fix the mistakes. They can easily recover the real message while everyone else struggles. So that's exactly how mec elise works. This type of cryptography built using error correcting codes. You already know error correcting codes are used in CDs, QR codes, and data transmission to fix mistakes if some bits get corrupted. In cryptography, we turn this concept into a security tool. So the difficulty task here is um, called decoding a linear code. In simple words, imagine you receive a message full of typos. If you don't know the rules of the code, fixing the message is extremely hard, right? But if you have a dictionary or secret rules, you can correct it really quickly. This is what mec elise secures. Outsiders see only a scrambled message full of errors when the rightful owner knows how to repair it. The scheme, the mec-Ellis crypto system, it was proposed in 1978 by Robert mec-Ellis. So it uses a special type of error correcting codes like GOPA codes. And you know what's amazing in this? After more than 40 years of attack, it is still unbroken. That's why it's considered quantum resistant. Advantages, it is very strong security record. Unlike RSC or ECC with quantum computers can break, mec-Elise has survived decades of cryptanalysis. No one has found a practical attack yet. It is resistant to both classical and quantum attacks. Even if quantum computers appears, mec-Elise is expected to remain very safe. Disadvantages, Public keys are very huge. RSA keys are few kilobytes. Lattice-based keys are a few kilobytes too. But MAC-LS keys can be hundreds of kilobytes to even megabytes. This makes it hard to use on devices with limited storage. And it is less practical for modern systems because of its key size. It hasn't been widely adopted, even though it's much secure. Next, we have is multivariate polynomial cryptography. This cryptography family, it is based on equations and equations. So imagine you are given a set of equations like x plus y plus z is equal to 10x plus y plus z is equal to 10x squared plus y plus z equal to 10x squared plus 25x squared plus 9 plus x. You are given a big equation. With a small number of variables, we can solve them. But in multivariate cryptography, there are hundreds of variables and the equations are quadratic, meaning they have like x into yx times yx power square, power 2, x square, and all like that. Solving such systems is hard, which means it is so difficult that even the best computers, the classical or quantum, struggle to solve them. And in terms of security, the strength comes from the fact that finding solutions to large quadratic systems is extremely hard. Even a quantum computer doesn't give much advantage here. That's why it was considered a good candidate for post quantum cryptography. So let's have an example here of rainbow. It is a digital signature. Okay, it was a candidate in the NIST competition for PQC, post quantum cryptography. Looked promising because it was fast and simple, but in 2022, researchers broke it by finding weakness. This means rainbow is not secure anymore. And the oil and vinegar scheme is the second, another scheme from the same family, still being researched but not yet trusted enough for standardization. And all the advantages, it's very fast, it is worth signing and verifying signatures can be done very quickly. It is also very lightweight. It could work well on smaller devices if secure versions are also found. And the disadvantages, the cons: unstable security. Many schemes that looked strong were later broken. Not reliable also. This makes people less confident in using it compared to lattice based or hash based cryptography. Hash based, we'll be seeing it now. And why it is less important, because of repeated failures like rainbow being broken, the cryptographic community does not trust this family as much anymore. So NIST focused instead of lattice based and hash based cryptography. Here we go, we have hash based signatures. Imagine you have a book of coupons, one time signatures, and each coupon can be used only once. So one term is XMSS. You must carefully track which coupon are already used. Sphinx, SPHINCS plus Sphinx plus. You have a magical way of generating coupons without worrying about tracking. Hashing ensures that once a coupon is used, no one else can fake it. So instead of relying on hard math problems like lattices or codes, these schemes rely on hash functions. Since hash functions are very well studied and widely trusted, this makes the system simple and secure. The core trick is that build one-time signatures using hashes and then organize them using a Merkle tree, a hash tree. So a good hash function is one way. You can't reverse it. And it is also collision resistant. It's hard to find two inputs that give the same hash. Even with quantum computers, the best that they can do is the Grover's algorithm, which gives a root power n speed up, right? And one example is that XMSS. So XMSS, in the sense, it is extended Merkle signature scheme. It uses one-time signature, and to allow multiple signatures, XMSS may many one-time keys together using a Merkle tree. It's stateful. The signer must track how many keys are already used. Sphinx plus, SPHINCS plus, uses a more complex structure that avoids the stateful problem. It is stateless, so you don't have to track key usage. It is standardized by NIST in 2022 as a backup post quantum signature scheme. Trade off: larger signatures and slower signing verification compared to XMSS or lattice based schemes. So this is all about post-quantum cryptography. Thank you.